Let's now talk about this central limit theorem problem involving a sum. A gambler makes 1,000 column bets at roulette. The chance of winning is 12 out of 38. There are 38 possibilities. 12 are winners. The others are losers. If the gambler wins, he wins $2. If he loses $1. Find the probability that if he plays this game 1,000 times, that the gambler comes out ahead and wins at least $0. To get started on this, we look at the expected value of any one play. So the expected value of x sub I. Well, we find the expected value. The possible values are 2 with probability 12 over 38. And the other possible value is -1, losing $1. And the chance of that happening is 26 out of 38. And so adding this up, we get 24 minus 26 for -2 over 38 for -1/19. So that's the expected value of any one play. Then the answer is negative because, of course, the odds are stacked against the gambler. To find the standard deviation, we first find the expected value of each x sub I squared. So that's equal to 2 squared times 12 over 38 plus -1 squared times 26 over 38. And this should have been a 38 here, of course, not a 28. Let me clean that up. So this should have been a 38 here. That was a typo. And so we get 4 times 12 plus 26 makes 74 over 38. Which is 37 over 19. And so the standard deviation of any one play is equal to the square root of 37 over 19 minus -1/19 squared. So we plug that into the calculator to get an estimate of about 5 decimal places, 1.39449 to 5 decimal places. The next thing we do is figure out the expected sum and the standard error for the sum, or the standard deviation for the sum. So the expected total, using the notation that we've used in class and in the textbook. Now this is going to be equal to n times mu, and in our case that's 1,000, times the average, which is -1/19. And so we plug that into the calculator to get -$52.63. The standard deviation for the total is equal to sigma times square root of n, according to the central limit theorem. So that's equal to 1.39449 times the square root of 1,000 and so plugging that into the calculator gives us $44.10, rounded off to the nearest cent. In other words, if we play the game 1,000 times, we expect to lose $52 or $53, give or take 44. So finally, the probability that the sum is at least 0 can be well approximated by the bell curve. The probability that a standard normal random variable, z, is greater than or equal to the observed total minus the expected total divided by the standard error for the total. And so just doing the calculation, get that z is greater than or equal to 1.1935, and then we use either the calculator or Microsoft Excel to figure out exactly what that probability is. Let me do this in Excel. The calculation on the calculator is approximately the same, so doing the calculations real quick. The mean, it was 1/19th, or negative 1/19th. The standard deviation worked out to be the square root of 37/19 minus negative 1/19 squared. So there's a standard deviation sigma. So the expected sum was 1,000 times mu. The standard deviation for the sum was the square root of 1,000 times sigma. And so the z value works out to be 0 minus the expected sum divided by the standard deviation, B4, divided by the standard deviation for 1.1935. And so the probability of this happening will be equal to 1 minus norm s dist of that number, which works out to be 11.63%. So finally we get that the answer here is 0.1163. So that's the chance of coming out ahead if the game is played 1,000 times. The answer is small. It is less than 50%, but it's not microscopically small. And that's kind of the appeal of gambling, that you can play the game for quite some time and there's still a very real, small but real chance of coming out ahead. All right, let's now change the problem from playing 1,000 times to 10,000 times. What changes and what stays the same? Well, one thing that stays the same is going to be that the first three lines here are still the same. The expected value for any one draw is still negative 1/19. The expected value of x squared, and the square here should have been inside of the parentheses. No big deal. Is still 37/19, and the standard deviation is still 1.39449. What does change is the calculation of the expected value and the standard error. So instead of a 1,000 here, we will now have a 10,000. So let me simply delete this, and in place we have 10,000. And likewise on the next line, this 1,000 becomes a 10,000. And so that will change a few things. So that changes this number here. It also changes the standard error, which in turn changes both numerator and denominator here, which will change this number here, which of course ultimately changes the probability that comes out. So the structure of the computation remains the same, but I now have 10,000 here as opposed to 1,000. So let's do the calculations again on the calculator. So 1,000 divided by 19. So now the expected loss is now $526 as opposed to $52. $526 and 32 cents. While if we take this number multiplied by 10,000, we now get 139.45. And so we put minus 526.63 here, and 139.45 in the denominator. The new z value that we get will be considerably smaller than, completely larger than we had before. 3.7743 according to my calculator. And then we once again use Excel to figure out the probability, the area to the right under the normal curve. So using Excel, this is now 10,000 here as opposed to 1,000. This number is also 10,000 as opposed to 1,000. So the z-value is 3.774257, and the probability of that event happening is about 8 times 10 to the minus 5. So 8 100,000ths, about 1 chance in 12,000 or so of coming out ahead. So this is an example of the law of large numbers. What ought to happen does happen if you do it long enough. You expect to lose money, and that's in fact what will happen if the game is played long enough.